Welcome to Brain Vision.
For the given problem, initially the capacitor C1, C2, and C3 form a series combination equivalent to a single capacitor, which we denote by 1, 2, 3, which we can write 1 over C1, 2, 3 is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And this gives us an equivalent capacitance 1, 2, 3 is equal to 2.4 microfarad. With the voltage V is equal to 12 volts, we obtain Q is equal to C1, 2, 3 times V, that is equal to 28.8 microcoulomb. In a final situation, C2 and C4 are in a parallel and are thus effectively equivalent to C24, which gives us 12 microfarad. Similarly to the previous computation, we use the equivalent capacitance C1, 2, 3, 4 is equal to 1 over C1 plus 1 over C24 plus 1 over C3. This gives us equivalent capacitance 1, 2, 3, 4 is equal to 3 microfarad. Therefore, the final charge is equal to Q is equal to C1, 2, 3, 4 times V, which is equal to 36 microcoulomb. For part A, this represents a change relative to the initial charge of delta Q is equal to 7.20 microcoulomb. For part B of the problem, the capacitor C24, which we imagine to replace the parallel pair, which are C2 and C4, is in series with C1 and C3, and thus also has a final charge Q is equal to 36 microcoulomb found in above. The voltage across C24 would be then V24 is equal to Q divided by C24, that is 36 microcoulomb divided by 12 microfarad. This gives us 3 volts. This is the same voltage across each of the parallel pair. In particularly V4 is equal to 3 volts, implies that Q4 is equal to C4, V4, that is 18 microcoulomb. For part C of the problem, the battery supplies the charges only to the plates where it is connected. The charges on the rest of the plates are due to the electron transfer between them in accord with the new distribution of voltages across the capacitors, so the battery does not directly supply the charge on capacitor 4.